Welcome back to another beautiful lesson of Pre-Cal. We're going to now deal with inverses of matrices, and we're going to see why it's important to know how inverses of a 2x2, but also an n by n matrix. We've done our REF, reduced row echelon of matrices. We've done solving linear systems using matrices. We've done so many other applications with matrices, like networking problems and so forth. But now we're going to do inverses and why they are necessary. Here we go. How do you find the inverse of a matrix? What is the inverse of a matrix? Let's look at the situation below. Okay, you've done these. You've been doing these kind of problems, right? Like if you have to solve for x and you're given ax equals b, for example, you're given ax equals b, right? Ax equals b. You know what to do. You would divide, because this is multiplication. You would do the inverse operation, which is divide. So you divide both sides by a, right? You would divide both sides by a, like when you were a kid, and you get x equals, I got it, b over a. Yay! Okay, so again, you were using inverses, but you just call them multiplication. The inverse of multiplication is division, and division, multiplication, addition, subtraction, subtraction, multiplication, addition, right? So you were doing that. So now, what do we do with inverses? Matrices. Pretend A and B are matrices, right? Let's pretend that these are matrices, okay? Now, the only way we can do these with matrices is, well, the same kind of thing, really. Ax equals b. So how are we going to solve for this x matrix, assuming that they're all matrices, right? So we're going to multiply A and B with A's inverse. What's the inverse of A? It's A inverse. So we're going to multiply both sides by A inverse. Same kind of thing. It's the same thing, right? Okay? But notice, and what do we get? What's A inverse times A? Well, we'll actually see it later too. But if you multiply the inverse and the A, just like in multiplication and division, like A over B, when you multiply B over A, you get 1, right? The identity matrix. You get the same thing here. So A inverse times A is going to give you 1x, and then you get this beautiful product, which is A inverse times B, and that product is going to be your x matrix. So A, B, and x are all matrices, really, okay? But the only thing that you have to keep in mind is if you multiply the A inverse on the left side, you have to multiply the left side of the B too. So left side, right, of the A, left side of the B. Okay, you have to multiply in the same position. So we'll do more cases of that, okay? All right, so let's keep going. Since there is no division in matrix, we use the inverse matrix. You're right, we can't just simply divide. So even if these are the same order, we can't be like B divided by A matrix. We can't do that. We have to multiply by its inverse matrix. So we'll formalize this. Let A be an n by n matrix, and let I sub n be the identity matrix n by n. You're right. The inverse matrices have to be an n by n or a square matrix. So I'll write that here. Square matrix, okay? So inverses only exist if they are square matrices. So let's do that again. Let A be an n by n matrix, and let I sub n be the n by n identity matrix. If there exists a matrix A inverse, there exists. That means sometimes it doesn't exist, so that means A inverse may not exist at times, okay? If there exists a matrix A inverse such that A times A inverse is equal to the identity, that means you'll get something like, if it was a 2x2, you get 1, 1, 0, 0, like this. It's an identity matrix, right? A sub A inverse is equal to identity matrix, or you can go the other way, where you multiply the inverse times the original A matrix, and you'll still get an identity. So I think I asked you this question before. If A and B are inverses, that's the only time that AB will equal BA. You remember I asked that when you were doing products, I said, does AB always equal BA? And I think a lot of you guys said no or yes, but maybe you didn't know exactly. But the only way they're equal is if A and B are inverses, okay? All right, so let's try some examples. Okay, make sure you slow down the video if it's going too fast for you and kind of digest the material, okay? All right, so let's do this. Let's actually go and do, okay. So a couple of other terminology and definitions. If an inverse exists, you remember how I talked about whether it does or does not have an inverse? Well, if an inverse exists for a matrix, then we say it's invertible or non-singular. Invertible means it's an invertible matrix, which means that it has an inverse, okay? Or we can say non-singular, right? Then what do you think we call an inverse? What's an inverse? Without, a matrix without matrix without an inverse, what is that called? Not non-singular, but you're right, it's a singular matrix. So if a matrix does not have an inverse, then it's called a singular matrix. All right, so part one, let's find inverses of a 2 by 2 matrix. 2 by 2 matrix is going to be the easiest one, okay? You can do it 2 different methods only for a 2 by 2. So 2 different methods only for a 2 by 2, all right? So 14 says, this is from the homework, okay? Find the inverse if it exists, okay? So I gave you this matrix. And we're going to call this guy an A matrix, okay? An A matrix. And we're going to actually, let's just, for in this case, let's give it positions like A, B, C, D, which is a pretty typical way of referring to each position, okay? All right, I'm going to show you 2 methods. I know you're going to like one way or the other better, okay? I'm going to show you method 1. Method 1, I'm going to show you the way that you kind of know. You already know how to do this, really. So this first method goes like this. You're going to try to do A, your original matrix, and you're going to form an identity matrix. What does that mean? You're going to set up, this is your setup, but you're going to convert this to look like this, where your I sub n is here, and then your A inverse is going to be on the right side. You see how they swapped? They swapped. Oh, so I know a lot of you guys are thinking, oh, what is that really doing? Ding, 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 ding. You're right. It's sort of like the reduced row echelon, except this side is not going to be just by n by 1. Okay? All right, so let's try that, okay? So we're going to go like this. So let's set it up. 1, 3, 2, 7. And we're going to go 1, 0, 0, 1. And we're going to hopefully swap these. Of course, these values will be different, okay? So let's try that. So but you gotta do a longer matrix operation now. It's actually a 2 by 4 matrix that you're solving. So again, this is a 1. So we're gonna make zeros again. So we're gonna multiply this by -3, and we're gonna add it to this guy. So if you're doing row by row operations, you're doing -3 R1 to create and adding it to row 2 to create your new row 2. Okay? So I'm doing that right now. Let's see what we end up with. I get 1, so -3, 0, right? Oh, sorry, 1, 2, 1, 0. This row doesn't change, right? And I get here 0, 1, -3, 1. Okay? Okay. Now I already have a 1 here, so I need to make a 0 here, right? It's almost an identity matrix, but not yet. So I'm going to multiply this by -2, and I'm going to add it to here. If you're doing row by row operations, elementary row operations, you go to negative row 2, or row 2. You're going to add it to row 1, and you get row 1, right? So last step, I think it's going to be last step. You're not doing anything to this row, so I write it first. I get 1, 0, 6, 7, and I get -2 here. And that right here is my A inverse. Ding, 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 ding. Okay, and that's it. That's how you do that, okay? Just for a 2 by 2 though. So my inverse matrix, so my A inverse, I can conclude it's going to be 7, -3, -2, 1. Okay? And let's actually see if that's true. What has to be true then? If I multiply A and A inverse, I should get 1, 0, 0, 1, right? So let's try that. So I'm going to go 1, 3, 2, 7 times 7, -3, -2, 1. Okay? I better get this or else. 7, -6, that's 1. -2, 2, that's 0. Woo! First row, complete. 21, -21, woo! -6, 7, yes! All right, so we did A inverse, and that equals an identity matrix. So we're good to go, okay? So that's the first method, okay? Second method might be a little bit new to you, but don't worry. So first method, we're going to call it the reduced row echelon method. The second method, we're going to call a determinant method. Now, determinant is something that we have not done so far, but we're going to get to it. So this method, we're going to call it determinant. I'm going to write it bigger. Determinant method. So let's write that bigger so you know exactly what this should be. Okay, we're going to do this a lot with the determinants later. Determinant method. Okay? Now, the determinant method you'll like better because it's simpler. But it only works for 2 by 2 matrices. Write that down, okay? Don't even try it for a 3 by 3 or an n by n. So here we go. Now, I'll give you the formula first. A inverse is equal to 1 over determinant times, look at this, I swap the D and the A, so D comes here, A comes here, and I negate the B and the C. Okay, it's simple as that. But you're like asking me, what the factor is a determinant? Determinant goes like this. For a 2 by 2, it's AD, so AD minus BC, the quantity. So let's do it for our case. What's our determinant of A? It's 1 times 7, right? Minus 2 times 3. And we actually end up with 1. Okay? So let's do the inverse now. That's the first step, okay? Second step, we're going to actually calculate the inverse. We better get this, right? We better get this. Because it's better be the same. Two methods, but same solution, right? It's going to equal 1 over the determinant, which is 1 in our case. Determinant, right? Our determinant here. Times, watch this, 1, 7, 7 and the 1 swap. So 7 goes here, 1 goes here. We negate the B and the C. So negative 2, negative 7. Oh, sorry, negative 2 and negative 3. Sorry, 7 goes here and negative 3. Okay, and we distribute this 1 to each of these and we multiply it. It's like a scalar multiplication. So we end up with 1 times 7, negative 3, negative 2, and 1. Remember, this can be something else later. When the determinant is 2, it'd be 1/2 times all these elements, okay? So watch. Did we get the same answer? Oh, yes, we did. So here's our inverse and here's our inverse. So let me ask you this. Which method do you like better? The determinant method or our REF method? Yeah, I don't think I need to hear the answer. Yeah, for a 2 by 2, definitely the determinant method is actually much quicker. Okay, well, good luck. Let's try one more with a 3 by 3, okay? Now, a 3 by 3, there's only one method, and the method is exactly what you've been doing. Okay, so part 2, let's find the inverse of a 3 by 3 matrix. There's no cool determinant method, there's only one method. Only one method, which goes like this. You start with your original matrix, you start like this. This is your setup, okay? And you're going to swap it, and you get something like this. You get I sub n here, and you get your A inverse on the side. And of course, you can check your answers after you're finished with your calculations with a calculator. The calculator, all you have to do is just set up your matrix A, right? Like the way you do it on your TI Inspires, and just go like this. Just set it to A inverse, and it'll do it for you. I'll show you in class too. Alright, so you guys, we're going to set up. I'm not going to completely do it with you because I know you know reduced row echelon very well. So you set up, this is your setup, 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay? Alright, now we're going to do RREF basically, right? Sort of like RREF. This side has to be the identity matrix. So they have to swap. Okay? So you know, you do your thing. You go negative 3, you add it to here. 1, you add it to here, right? And ... you complete all that and turn off your computer and come back to it, okay? Welcome back. The moment of truth. Did you get something like this? Did you get something like this? 1, 0, 0. You did all your reduced row echelon operations, and I hope you got an inverse of negative 13, 12, negative 5, 6, negative 5, 2, 4, negative 3, 1. Is this what you got? If you did, then you would be correct. Well, you can always checky your answer, right? How do you do it? You can go A inverse, does it equal the identity matrix? Identity matrix is also your vocabulary word, okay? So make sure you've got that, okay? Or you can multiply the other way too. A inverse, or A inverse A. You should always get the identity matrix. Okay, so if you're having trouble with the RREF, let me know, and I can help you with that. But I'll see you next time. Bye.